Alright, welcome to this last video of Unit 2 where we're going to learn about moles. And I'm not talking about the moles that are on your face or the mole that's in your yard, but we're going to talk about what a mole is. We're going to learn it's kind of like the word dozen. And we're going to talk about how we can use that to help us better deal with quantities of atoms. And so the mole is the SI unit for the amount of a substance, and the number of particles in a mole has been experimentally determined. And so that number is the number of particles in one mole of a pure substance is known as Avogadro's number. And so we're going to talk about what this number is here in a moment, but it essentially is this number. And so 6.02 times 10 to the 23rd is the amount of particles that are in one mole. And so I want to go ahead and pause for a moment and talk about how that is compared to the word dozen. And so when I say I have a dozen of something, that means that I have 12 of that thing. If I say I have a mole of something, that means I have 6.02 times 10 to the 23rd of that thing. And so if we have a mole of atoms, we have that many atoms. And so the reason why we use this concept of a mole is because atoms are very, very, very small. And so that means if you have even a little bit of substance, you're going to have a lot of atoms. And so it's inconvenient to deal with these numbers. And so just like we sometimes talk in terms of dozens, we're going to talk in terms of moles. So let me ask you this: if I had 2 dozen, how many items do I have? Well, I have 24 items. So if I had 2 moles, I would have 6.02 times 10 to the 23rd times 2. All right, so that happens to be this number right here. It's a very, very large number, and again, that's 1 mole of substance. So 1 mole of anything is 6.02 times 10 to the 23rd particles. Now you can change that word particle for atoms or molecules or ions, which we'll learn about ions later. But essentially 1 mole of anything is 6.02 times 10 to the 23rd, just like a dozen eggs or a dozen donuts or a dozen chairs. Whatever you're using the word dozen for means 12. All right, so let's talk about mass though. So the mass of 1 mole of a substance is called the molar mass of that substance. And so the molar mass, the units for that are going to be grams per mole. And so it tells you how many grams there are in a mole. And the molar mass of an element is equal to the atomic mass. So again, the molar mass of an element is equal to the atomic mass. And again, we find the atomic mass on the periodic table. So for example, the molar mass of silicon is 28.086 grams. So that means if we had 1 mole of silicon, we would have 28.086 grams of silicon. Now, if we had 2 moles of silicon, we would have 28.086 times 2. Now, something that I want to really highlight is, what if we had a dozen chairs and a dozen donuts? Which one do we have more of? So which one do we have more of? Well, we actually have the same. We have 12 of each. But are they the same masses? And the answer is no, because if we have a dozen donuts and a dozen chairs, the chairs are probably have a greater mass. The chairs probably have a greater mass, unless you have some giant donuts or something, or maybe you have little itty bitty chairs. I don't know. But my point here is that a mole of silicon and let's say a mole of carbon, if you had a mole of silicon and a mole of carbon, you would have the same number of each atom. You would have 6.02 times 10 to the 23rd of that atom. However, if you look at the molar mass of silicon, the molar mass of silicon is much larger than the molar mass of carbon. In fact, carbon's is 12.01. And so that means that for 1 mole of carbon, you'd have 12.01 grams of carbon. That's compared to 1 mole of silicon is 28.086 grams. And so again, if you have 1 mole of carbon, 1 mole of silicon, you'll have the same number, but different masses. All right, something that we need to keep in mind is diatomic elements. And so we need to remember the phrase Hofbrinkel. The phrase Hofbrinkel tells us all of the elements that are in a given, or I'm sorry, all of the elements that if they are alone by themselves, they don't exist as one but two. For example, oxygen gas is not O, it's O2. Fluorine gas is not just F, it's F2. And so if we're going to take, for example, hydrogen or oxygen gas, which is O2, that means there's two oxygens, because oxygen won't just exist by itself in its elemental form, it'll combine with another oxygen. And one oxygen, if you look at your periodic table, has a molar mass of 15.999. However, because there's two oxygens, it's not 15.999, it's 31.998, because you have to multiply it by 2 because there's two of those elements. So again, the word Hofbrinkel, whenever those elements are alone by themselves, will exist in pairs. Now again, it's when they're alone by themselves. If we think about water, water is H2O, there's only one oxygen, and so if it's in a compound, if it's chemically bound with something else, it's not necessarily going to have two. It's only when it's alone by itself that it will be guaranteed to have two. So we got to keep in mind Hofbrinkel. All right, so chemists use molar mass as a conversion factor in many chemical calculations. And so let's go ahead and take a look at this flow chart here. This is going to be another one of those topics where it's going to be really important that you watch the guided practice problem, that you really understand the guided practice problem. We're going to be using this flow chart for the entire year. And so it's going to be really important to get this down. And this is kind of like converting in the metric system, or just regular conversion. So in Unit 1, we learned about conversions, and this is where we're going to start using units that we're not so familiar with. So what I want to do is talk about what this flowchart is. If we are given atoms, we can take atoms and convert them to moles. If we're given grams, we can take the grams and convert them to moles as well. Notice how if we go from atoms to moles, we're using Avogadro's number, which is 6.02 times 10 to the 23rd. And notice when we go between moles and grams, we're using the molar mass, which is the atomic mass from the periodic table. And so notice how the middle there is moles. So moles is in between atoms and grams. And so if we are ever given atoms and we're asked to calculate the grams, we will always have to go to moles first. We can't go directly from atoms to grams. We have to go from atoms to moles to grams. Just like if we had kilometers and we wanted to go to centimeters, we would have to go from kilometers to meters to centimeters. And so this is the same thing, the same situation. If we're given grams and we're asked to go to atoms, we have to go from grams to moles to atoms. However, if we're given moles, we can go to either of them in one step. And so again, this is going to be something that's going to be really important that you pay attention to the guided practice problems so that you can really get down the method here. Because again, this is something we're going to use for the whole year, and we're actually going to expand on this flow chart next semester, and so it's going to get really cool. So, well, watch the guided practice problems, and if you have any questions, feel free to email me, and you guys have a great day.